So I am from City University of New York. So we call it CUNY, and CUNY has many different campuses, 25. And my home campus is Queens College. And also I have affiliation with the Graduate Center, which is right next to this place. And also I started some visiting position at Korea Institute for Advanced Study from last year. I want to thank my current and former group members for their contributions, and also many of collaborators. And the research I am going to talk today was mostly funded by National Science Foundation and the Department of Energy of USA. Before I give a talk, I want to introduce you to my recent book that I have written. And so Jeff Sina at Oregon, and also the George Schatz Northwestern, they gave pretty generous and nice testimonials for this book. And I think this is probably good for physicists to learn about quantum chemistry as well. So this was meant for chemistry students, but I think it will be also useful for many physicists who want to learn how the quantum chemistry problems are approached. So I'm going to first talk about more general things of quantum mass equations and Polaron transformed quantum mass equation approaches. And then we'll talk about partially Polaron transformed approaches. And then after that, I will also talk about Caldera-Leggett quantum Fokker-Planck equation and its generalization that includes some non-Markovian effects. And if I have more time, that I'll be also talking briefly about my work on generalized mass equations that can be applied to light-Hibbeson complexes. So all of these are a bit kind of old because I've been mostly focused more on a little bit different theories very recently. But it doesn't mean that I stopped working on this. Actually, they are really close to my heart, and I keep working on that. But so I guess in a couple of years, I may have more updates. So I don't really have to explain this to all of you, but I want to clarify some terms. So when I say quantum mass equation, I define it as the time evolution of a reduced density operator. And my definition of mass equation is time evolution of populations. And on the other hand, the quantum Fokker-Planck equation, I mean by phase space representation of quantum mass equation. And of course, there are many other important methods that we here learned about, path integral approaches and also the tensor approaches. And it was really exciting to learn more details of recent advances. So let me start from pretty much, things that most of you may know. So the quantum mass equation, some of the oldest ones and very well-known ones are Markovian versions, Lindblad or Redfield equations. And Lindblad equations are written down based on some mathematical requirements, but Redfield equations were derived by making second-order approximation and so-called Born-Mark approximation. And when we say Markovian, it actually means that the relaxation tensor is time independent. And so it is known that no Markovian quantum mass equation satisfies all of the following three requirements. And so if you want to make the Redfield equation positive by introducing secular approximation, but then it actually ignores some non-resonant terms. And this results in violation of the third property. And Lindblad equation can be made to satisfy either two or three, but not both. So the Lindblad equation, as all of you know, it has this form. And so this form of quantum method equation is necessary and sufficient condition for the direct product of the reduced density operator and identity operator for its reservoir to remain always positive. So that is the statement of complete positivity. And so this is actually based on the assumption that the bath induces instantaneous relaxation and also instantaneous entanglement of the system and environment. And this is actually physically possible only when there is some kind of coarse graining in time, because nothing is really instantaneous in quantum world. So as some of you actually mentioned earlier today, so this is quite well-known paper, and Petrukas actually states that reduced dynamics need not be completely positive. So let me go through his logic a little bit. So what he actually rediscovered was that if you think of a mapping from reduced system density operator to another one, then the properties of the mapping has to satisfy these three properties. It has to preserve the mixture, and also it has reproduced the original system density operator. And it is also positive for all positive system density operator. And by considering two-state system, he actually proved that the only mapping that satisfies all these three properties are direct product map. However, he also stated that product map is valid only for weak system math coupling, and it does not represent many important and real physical situations. Therefore, he concludes that complete positivity has to be abandoned because other properties cannot be given up. And this is possible probably by limiting the domain of system state. And then LP actually wrote a comment that complete positivity is essential in finding the exact condition for the positivity preserving domain is not possible. Rather, condition A or B can be given up. But then Petrukas replied that there is more serious problems in giving up A or B, and it is probably okay to give up complete positivity for practical purposes. So there have been many papers that actually followed up on this. And nowadays, there are Lindblad type equations that are derived from some kind of coarse graining. But I think that, however, this fundamental issue remains unsolved. So I kind of use this as a background for my approach because still it's less satisfactory formally, but at the second order level, probably non-positivity or it's difficult to prove if we actually include inhomogeneous terms and also time-dependent relaxation tensors. So it's uncomfortable. This makes us feel uncomfortable because there is no guarantee. But practically, if you actually choose the right second order method with inhomogeneous terms, it seems that practically they work pretty well. Of course, now there are more advanced approaches, except for the tensor, approaches that were mentioned a lot today, and also the path integral approaches that Nancy have worked on decades. There are also other approaches like hierarchical equation of motion approaches, which is also, again, another way of solving unprojected parts by keep making hierarchy of equations. Or another approach that I'm not going to talk about, probably Victor Batista may talk, is the generalized quantum method equation approach, where it is also solving the unprojected parts by solving integral differential equation. So they are all different flavors of numerical solution for trying to get the exact ones. So my goal some years ago had been more modest. So I wanted to actually work on large systems, and I didn't really care that much whether I should sacrifice the efficiency to get a little bit of efficiency. So all I wanted was a reasonably good method that can be applied to a wide range of parameters and for big enough systems. So in that case, so what I learned from my then mentor, Bob Silve, was that it is actually possible to improve the accuracy of the second order quantum method equations by moving to a picture or frame that makes the system-based coupling small. And a good example for this is the Polaron transformation. So Polaron, the idea of a Polaron is very, very old. So it was actually worked on by Landau, Fraley, and Holstein and Feynman. And Polaron actually means the dressed state for charge carriers, or maybe excited state. And so if you have the bare state, and if they are dressed by the environment, then it turns out that the effective coupling becomes smaller. So the electron coupling or the coupling between the two quantum systems becomes renormalized. And the reduction is because of the Frank-Condon overlap factors of the two displaced operators in these cases. And long time ago, Silve and Harris and also many others actually worked on these things. And then they worked on applied this concept to excitation energy transfer and also came up with unified treatment of incoherent and coherent dynamics. So it was actually possible to extend that idea a little bit more for general situations. So what you do is that you first make Polaron transformation, and this is system-dependent displacement of harmonic oscillator path. So in the entire system and path degrees of freedom, it still remains as a unitary transformation. So nothing really changes by making that unitary transformation. And in fact, Feynman also works on Polaron transformation in path integral formalism. And that's also an alternative approach of getting the Polaron ideas. And then once you do that, you can redefine a small perturbation term by subtracting the average system-based interaction term in the Polaron picture. And then you apply the routine projection operator formalism and make perturbation approximation to obtain a practical time-dependent quantum method equation. So important details that shouldn't be overlooked is that the initial condition and physical observable should also be transformed the same way, because if not, you are actually changing the nature of the problem. So the resulting Polaron transformed quantum method equation has this kind of form. So since 2008, I've been working on different extensions and versions of the Polaron transformed method equations. And also, similarly, Yuan-Cheng Jang now at Taiwan and Ashan Naza right now at Manchester, and Jian Shao and Ivan Kazal. So they have also worked on this Polaron transformed quantum equation, including Eric also who talked about some of that this morning. So this book actually provides all the derivation of quantum method equations up to the fourth order with complete formal expressions, and also explains a little bit about the quantum Polaron transformed quantum method equation. Some of the applications that we used, the approach was to the external dynamics from this unit to this one. And they did polarization anisotropy measurement and then found that there is oscillation of the signal with about 1 picosecond period. And if you actually do the quantum chemistry calculations, the actual coupling is predicts that the oscillation has to be faster. But then we found that the effective coupling is reduced by the high frequency mode. And also the low frequency mode ends up slowing down the dynamics. So things like B or C seem to represent the experimental situation. So the paper actually kind of provided good theoretical justification of the experimental measurement in this case. And another benefit of the Polaron transform approach is that it is actually applicable to more general case of the system-based coupling. So in this case, so the model actually represents the torsional modulation. The model looks kind of similar to the spin boson Hamiltonian, but the difference here is that J is actually a function of phi, and here phi is also given by the linear combination of oscillators. So this model actually represents the physical situations where you have the donor and the acceptor, and they go through some small amplitude oscillations. And depending on the value of phi 0, as you can see here, they can be oscillating around the parallel positions, or they can be oscillating around the orthogonal positions. And initially, we actually used this model to also figure out whether the torsional modulation has an important effect for the DTA that I just showed. So we conclude that it's not really the major effect. However, the additional dynamics calculation actually show that the torsional modulation in general increases the phasing and relaxation rate. And also the details of the amplitude and reference angle have important effects. So this extends the conventional model and to more general situations. And this kind of situation actually happens a lot in many organic molecular systems. And another interesting TOE model is this donor bridge and acceptor model, because this kind of situation happens a lot. So what is normally described is that when the bridge energy is very high, the mechanism is through the super exchange. When the bridge energy is low, the mechanism is through hopping. This one actually shows that the Polaron transform quantum master equation in fact interpolates between the kind of the oscillatory coherent dynamics. And then, of course, when the bridge energy becomes very high, somehow the dynamics based on the Polaron transformed approach is somehow a little bit in the middle. And so from the oscillations, you can see that in the weak coupling limit, this Polaron approach actually agrees well with the Redfield equation thing with secular approximation as it should. And then in the strong coupling limit, it agrees with the hopping equations. And then in between, there is, yes?
Sorry, I didn't want to interrupt you in sentence, but on the previous slide, your definition of phi, that's supposed to be a number, I guess?
No, it's an operator, actually.
It's an operator.
Yeah,
so
yes.
This sign of, okay.
Yeah. So here, everything, J, if I put this as the operator, that it might have been more obvious, but yeah. Yeah, in this case, it's an operator. So it's the lowering and raising operator of the oscillator. And then there is actually additional Bethe operators. So this is actually a combination of both the operator that comes here, and also there is additional the side diagonal coupling. So it has two kinds of Bethe. One is modulating the coupling, and the other is modulating the energy of each side.
What is the physical basis for this type of the J form?
So you have the torsional motion, right? And then the torsional oscillation will change the electronic coupling. And then the torsional mode will be also coupled to other vibrational modes. So if you do normal mode transformation, this is how you get. So from the dynamics calculation, we can actually extract the effective rate. And as you can see that there is actually interesting turnover from the super exchange limit to the hopping limit. And this one actually shows that in the intermediate situation, there is some enhancement due to quantum effects, although it's not always easy to distinguish that from incoherent behavior. So there is some important and subtle enhancement due to quantum effect. Yeah, so this is more another case of the multi-state situations. Again, this one shows that fast coherence transport occurs in the very short limit. So I show the examples where there are only few states, but Yuan-Cheng Chang actually worked on maybe hundreds of states. And the nice thing about this Polaron approach is that you can actually simulate pretty big systems at the cost of the second order equations, but still you can actually reproduce both weak and strong coupling limit. And hopefully in the intermediate situations, it is actually reasonably accurate. But there are issues, yeah.
What is the initial condition of the bath? The initial condition of the bath.
Initial condition of the bath, in this case, so the model calculations I did, so I used the product initial state between system and bath, but the formalism actually can be applied to more general situations. So the equation itself can be applied to any kind of the coupling between system and environment.
So the bath is not necessarily in equilibrium with the donor state initially.
Yeah, that's true. Well, of course, I think all the difficulties, when it comes to actual applications, there are always some numerical difficulties that one has to deal with, but the formalism itself is general. I was actually more concerned about a little bit more fundamental issue is that it's not actually for any kind of bath, because for slow bath modes, it actually the Polaron transformation over relaxes the bath response. Therefore, it actually tends to suppress the coherence terms prematurely, and therefore it's not really accurate for slow bath. And also for ohmic bath, there is not so much additional improvement. So to address this issue, there have been variational Polaron transformed quantum mass equation or frozen mode approaches that they are actually quite successful. So I recommend you to use these kinds of approaches because they are well established at this point. However, I was more interested in actually making this approach more straightforward and more systematic. And that for that, I came up with this partially Polaron transformed quantum mass equation approaches. So let me go through a little bit more detail of this so that I can actually give you more theoretical description of the Polaron transformation in general. So let's say you have this kind of system bath Hamiltonian. It's multi-state generalization of spin boson Hamiltonian. And then if you make the Polaron transformation, then it turns out that the system energy becomes normalized. And then here JK is the average coupling after the Polaron transformation. So you subtract and add. And so this, you treat this one as the zeroth order system Hamiltonian. And then the whole thing becomes the zeroth order Hamiltonian. And then this term becomes the first order Hamiltonian. And if you actually don't have this W term, it becomes Polaron transformed quantum mass equation. But by introducing weighting function, it becomes partially Polaron transformed equation. So here, this actually can account for two situations. You have separate modes. Some are Polaron transformed and others are not. Or actually, even for the same mode, it can be partially Polaron transformed, depending on the frequency. So you go through this formalism and then simply apply the projection operator formalism. Then you get this general formally exact time non-local equation. And in fact, the idea of Polaron transformation is not incompatible with other advanced approaches, because at this stage, you can also apply hierarchy, generalized quantum method equation, or even tensor methods, because the structure is the same, although the expressions are a bit more complicated. What will be the benefit? Because of the transformation, I think that it will have short iterations. It will require short iterations, and maybe there can be some advantages of starting from this equation. Of course, you can also convert that to time local form by using the inversion that was explained in this paper by Shibata and Arimitsu. And then you obtain the time local equation, as you can see here. And so whether it's time non-local and time local, as long as it's time dependent, they all explain the non-Markovian effect. And then once you have this time local equation, it is actually convenient to make the second order approximation by truncating all the terms beyond second order. And then when you do that, you come up with these inhomogeneous terms. And interestingly, at the second order, this actually additional term that comes from the inversion in the unitary time evolution actually disappears. So these terms actually make contributions only at the higher order. And so that's why the second order equation becomes a bit simpler. So these are some examples of the relaxation tensor. And actually, these are general expressions. What you can see is that the first term actually accounts for the Polaron transformed part. And this accounts for the untransformed part. And then the third term terms are cross terms between the two. So if they are independent of each other, then the cross terms disappear. But if the same mode is partially transformed, then you also have these cross terms. And also the inhomogeneous terms are a little bit more complicated. So this is, for example, the first order one. And the second order terms can be all expressed in terms of all these things. So in a sense, they are more, different kind of very simple tensors that you can easily calculate without any iteration. So I did, as the first kind of test, I did the simple calculation for homogeneous terms without actually including the inhomogeneous terms, because without so much benefit, they are much more time consuming to calculate. And so these are some examples. So what you see is that, in fact, depending on here, actually, this is the form of the weighting function that I find that works well. Because when omega becomes 0, it actually scales like omega square. And when omega is very large, it scales like 1, it becomes 1. And depending on the frequency of this partial Polaron transformation, what you see is that there is smooth transition from the incoherent behavior to coherent behavior. And so this is the case of the donor and the acceptor having the same energy. This is a case where the donor have a little bit higher energy than the acceptor. What you see is that, in fact, the extent of the partial Polaron transformation also changes the steady state limit in this case. So these are results that I have, numerical results that I have so far, but still there are a lot to work on in this partial Polaron transformed quantum mass equation approach. And so what I wanted to say was that the Polaron transformed quantum mass equation with time-dependent relaxation super operator and inhomogeneous terms works well in both weak and strong coupling to Beth. And I So, and also I talked about general expression of the partial Polaron transform quantum mass equation, and it is actually applicable to broad range of open system quantum dynamics, including external and charge transport dynamics. And it seems that if you choose the weighting function properly, it's actually possible to modulate and also the adjust the coherent behavior and steady state limits. And this actually gives an idea of using variational principle with those partial Polaron transformation as another knob. And so the next level I'm going to talk about, I'm going to actually work on is to come up with a few ideas for variational approach. And also another interesting thing is that when it comes to quantum sensing and control, now we have to think about the time dependencies in both system and system-based couplings. So in these cases, the Polaron approach and partial Polaron approach are actually quite easy to be extended in those situations. So how much time do I have?
You're doing okay on time, another 5 minutes.
Another 5 minutes, okay. So let me then go through quickly the Caldera-Leggett quantum mass equation and quantum Fokker-Planck equation. So it is actually really great paper that shows how one can derive the quantum Fokker-Planck equation from the path integral formulation. And the assumption that is being made here is that the best correlation functions, the real part behave like delta function and imaginary part behave like the derivative of delta function, then you get this equation. And if you actually convert that to Wigner distribution, then you get Caldera-Leggett quantum Fokker-Planck equation. So it's actually the same as classical Fokker-Planck equation, except that you have this quantum force. And it has been used, for example, to study decoherence. And also, it was also demonstrated that it can be used for numerical simulation of few dimensional systems. But there are issues with Caldera-Leggett equation. First, it's non-positive definite. And also, if you look at the study of formula derivation a little bit, it turns out that it uses both a high temperature limit and Markovian approximation, but it may actually end up being unphysical in some way because it requires this kind of two different conditions. And it may apply to certain macroscopic quantum systems, but maybe not for actual molecular systems. So it turns out that it is actually possible to correct this quantum Caldera-Leggett equation by including the next order of non-Markovian effects. So let me just run down the equation a little bit. And so for this, I actually started with more general photo-induced excited state dynamics. So you just go through the standard path integral expression and including the influence functional for the ground state, imaginary time, and real time influence functional. Then you can get this formal expression and then integrate over the all the Bath environments. Then you get this non-equilibrium influence functional. So these two these terms represent the excited state real-time dynamics. This represents the imaginary time, the ground state thermal distribution. And there is also interesting coupling term between the two. And so these are actually expressions. And so what I did was, why don't I actually expand the Q prime and Q2 prime around T1 up to the second order, and then do the partial integration. Then it is possible to actually convert the double time integration into single time integration. If you do that, then it is possible to derive the equation, time evolution equation. So these actually include the next level of approximations. And So these are the final expressions. And there are some interesting boundary terms, but they disappear. They do not contribute for large time. So the way you do that is that if the influence functional consists of only single time integrations, you can actually divide that into small pieces. And if you can divide that into small pieces, then you can express the reduced system density operator this way. So in this expression, you make the first order derivative, first order expansion, and then you do the second order expansion, and then do the Gaussian integration in complex domain. Then you get this kind of equation. And then, so the final form actually turns out to have additional terms that are missing in Caldera-Leggett equation. And these actually additional terms make the equation positive as long as the temperature is high enough. So for example, as you can see that except for very low temperature limit, in the steady state limit, the positivity condition is actually satisfied with this equation. And you can also convert that into quantum Fokker-Planck equation. And also in the intermediate and high temperature limit, it is possible to come up with simpler and also steady state quantum Fokker-Planck equation that actually account for some non-Markovian effects in average manner. So the summarizing, so I think that it is possible to extend the Caldera-Leggett quantum Fokker-Planck equation by including additional terms that also satisfy the positivity condition. And also it may be possible to develop Langevin type of equations starting from that quantum Fokker-Planck equation. Maybe for the remaining 1 minute, let me quickly go through another interesting approach. So this is actually also including the master equation, non-Markovian effect, but within the population dynamics. And it is actually using this kind of projection operator. For within each model, actually you can use any kind of quantum dynamics methods that you like. And so using this approach, we actually calculated the population dynamics of X-term from one to the other. What you find is that at low temperature, there is significant non-Markovian effect. But at high room temperature, the difference between Markovian and non-Markovian is small. You extract effective rate, then what you find is that around the room temperature, the non-Markovian effects are not really that significant. And we also use that approach to calculate the effective rates and sample that over 10,000 realizations of disorder. And then we came up with this estimate for the diffusion length about 100 nanometer length. And the theoretical range of the extern transfer between the two was this range. And it turns out that very recent work by Doran Raka group, they used the approach called ad hoc, and then their results are actually quite consistent with our simpler approaches. Now, of course, this also shows the distance dependence. What is interesting is that in this system, in the case of LH2 complexes, in fact, when they are very close, there is in fact factor of 10 enhancement due to quantum delocalization of the extons. And I think that actually explains why it has fairly strongly coupled chromophore system. But on the other hand, also what you see is that the reduction, there is reduction by a factor of 4 because of disorder. And when you also include the effect of disorder, all the interesting non-Markovian effects disappear. So for theoreticians, it's quite disappointing, but I think that's also how maybe a lot of nature works. And finally, I want to kind of show this review paper because I think if you see, you will find pretty well validated models, quantum models for these three complexes. And in this work, we also provided a review of key experimental and theoretical results, and also a comprehensive description of all quantum mechanical principles and calculations. And I believe I kind of alluded to important design principles. And this is my final slide, and then I'll be happy to answer any of your questions.
A quick one. What was the spectral density in the LH2 calculations?
Say it
What
again.
was the spectral density in the LH2 calculation?
Yeah. What kind of spectral density did I use? So for the LH2, we used the spectral density that we determined from the spectral line narrowing experiment. So it is combination of ohmic and also super ohmic parts.
Super ohmic or
It's the mix of ohmic plus super ohmic.
so the line narrowing experiment? Sorry, the
Yeah.
line narrowing experiments have produced 50 vibrational modes with boundaries factors. That's not what you're using.
Yeah, maybe you are talking about different things, but for LH2,
I'm talking about the bacterial chlorophylls.
yeah. So I think so the calculations I did was actually based on the spectral densities that were available around 1999. And then after then, there have been more recent spectral densities and also additional also computations. So it remains an important issue, but I'm pretty confident myself that the results we got are kind of not sensitive to those details of the spectral densities, but it remains to be confirmed and tested. Yeah.
Jonathan?
So with the partial photon transform approach, how does this relate or differ to the variational photon master equation stuff that As and Nazir has done?
I think eventually it may lead to general and simpler variational approach. So the variational approach that Ashan Nazir did was actually based on the old ideas by Silvey and co-workers. And they used the Gibbs-Bogoliubov variational principle to minimize the free energy. I'm not sure whether that is really, sometimes it may be physically relevant, but I think that in my case, the extent of the polar transformation may result from the competition of the in bath dynamics and initial population transfer. So it's not yet variational, or it may not, the variational approach may not even be necessary. So I didn't yet explore that. So I think there are a lot of interesting questions to explore at this point. But before doing that, I had to actually kind of complete the partial polar transformation formalism first.